The problem states, let R be the region in the first quadrant bounded by the x-axis in the graphs of y is equal to ln x and y is equal to 5x, as shown in the figure above. If we look towards part A, the question asks us to find the area of R. We will solve this problem by using two integrals, one for measuring the area under the graph y is equal to ln x, and the other for measuring the area under the graph of 5 minus x. You can measure the intersection of the two lines by setting the equations equal to each other. So under part A, you would write ln x is equal to 5 minus x. You can solve this on your calculator if you have a TI-89 by using the solve function. So you'd press F2, 1, and then you type in the equation. So it'd be ln x is equal to 5 minus x and then comma x because you're solving it in relation to x. So if you wait a while, you'll eventually get the value x is equal to 3.69344, which you can also denote as a, and you can do this on your calculator too by first writing 3.69344, then pressing the still button and then pressing in any variable. So I'm just going to use the letter A for right now. And voila, you've just stored a variable. And after that, you found the intersection point. You can set up the integral. So basically, you use the intersection point as an endpoint between the two integrals. So the first one would look like 1 to a, because that's your x values. And then you write in ln x because you're trying to find the area under the graph of ln x, dx plus a to 5 minus x dx. You would get 1 point for the integrand, 1 point for the limits, and then if you solve it, you would get another 1 point. So you can solve it by first pressing F3. So it's F3, and then going down to NINT. Now you can just type in the expression. So it's ln x, and then comma x, and then 1 a. You can do this same thing for the second integral, so it'd be NINT 5 minus x, comma a 5. So you get the value of 2.9858. Now, if you go down to part B says, region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. Right, but do not solve an expression involving one or more integrals that gives the volume of a solid. So you can actually tilt the graph on an axis. So if this is now the y-axis, then the graph would look something like that. So that'd be region R. Now, if you draw squares on top of it, you can get a visual representation of what it would look like. So there we go. That's our visual representation. Now, if you draw the actual squares out, and you can see what the bases would be like. So if the x value were between 1 and a, the base would be ln x, and if the x value were between a and 5, the base value would be 5 minus x. And so you can write this in an integral basically the same way you wrote it in part A. So it would be, once again, 1 to a dx plus a to 5 dx. But instead of it only being ln x and 5 minus x, it's actually ln x squared and 5 minus x squared because you're trying to find the area. And the area of a square is just the side squared. So it's ln x squared and then 5 minus x squared. And that would be equal to the volume. You would get 2 points for the integrands and then 1 point for the volume expression. Now moving on to part C. Part C says the horizontal line y is equal to k divides R into two regions of equal area. Right, but do not solve an equation involving one or more integrals whose solution gives the value of k. So basically, the easiest way to solve this problem would actually be to tilt the graph in relation to the y-axis and not the x-axis. So you would basically see the graph like this. Now, since you'd also be tilting the graph like that, you also have to solve the equations y is equal to ln x and y is equal to 5 minus x in relation to x and not y. So it'd be x is equal to e to a y, and x is equal to 5 minus y. And so basically, if you tilt this again, you're trying to find the area of this, like this, horizontally. And so it'd be the integral of 5 minus y minus ey, because this is 5 minus y, this is ey, dy from 0 to k, because there's a line over here labeled k, is equal to half of the area of R. And we've already solved for the area of R in part A above, which gave us the value of 2.9858. So the final would look like 1/2 of 2.9858 is equal to k05 minus y minus ey dy. So this would basically be your final answer. You would get 1 point for the limit, 1 point for the final equation, and 1 point for the integrand. Other area and cross-sectional volume problems include 2007, 2008, number 1, 2009, 2010, number 4, 2011, number 3, 2013, number 5, 2014, and 2015, number 2.